All right, this is a video tutorial on the Big Ideas Geometry section 2.2 Inductive and Deductive Reasoning. So your two learning objectives for this one are pretty self-explanatory. You can use deductive and inductive reasoning. So two major core concepts in relation to inductive reasoning. First is a conjecture. It is an unproven statement that is based on observations. Last time when we talked about finding true and false statements with our conditionals, a conjecture is something that is unproven just because of the observations that you're making. There's no formulas, there's no rules. Usually it's going to be based off patterns, and that's what we use with an inductive reasoning. They're used when you find a pattern in a specific case and then write the conjecture for the general case. So you're looking for a pattern using inductive reasoning. Then based on that pattern, you're writing a conjecture on this case. So based on the three diagrams below, there is a pattern that may be occurring, and we need to figure out what the fourth figure in this pattern will look like. So figure one is a circle cut in half into two semicircles where one of them is shaded. Figure two is a circle that is cut into four equal parts where one of the sections is shaded. And figure three is cut into six equal parts where one of the sections is shaded. So one way we can look at that is to just count how many parts are in each circle. So we have 2 in the first one, 4 in the second one, and 6 in the third one. So the pattern based on how many parts are going to be in each figure looks like that each circle is divided into twice as many regions as the figure's number. So figure 1 times 2 gives us 2 parts. Figure 2 times 2 gives us 4 parts. Figure 3 times 3 gives us 6 parts. So figure 4 times 2 would give you 8 parts. And that horizontal line will help indicate what area is going to be the shaded one. So in figure 1, it's above the horizontal line. Figure 2, it's the first one on the left above the horizontal line. Figure 3, first one on the left above the horizontal line. So you're going to shade that section above the horizontal segment on the lefternmost part above the horizontal line. And that would be your fourth figure. Another example, numbers such as 3, 4, and 5 are called consecutive integers. Whenever something is consecutive, they are back to back, right next to each other in order. So make and test a conjecture about the sum of any 3 consecutive integers. So the solution that you would be able to figure this out is to find a pattern using just a few groups of some small numbers to make it easy on yourself. Now, obviously, you could pick any 3 consecutive integers. So if you want to do hundreds, 123, 124, 125, you certainly can, but let's make it easy on ourselves and just pick some small numbers. So if we start first with 3, 4, and 5, the sum of those consecutive integers would be 12. Okay, let's try and look at another set, 7, 8, and 9. Again, you could pick a different set, but I'm just going to pick these because they're small and they're easy. Add those 3 together and you get 24. 10, 11, and 12. You add all 3 of those, you get 33. 16, 17, and 18. Adding all of those up for a grand total of 51. Okay, what are some patterns that we notice about those? Well, the answer for 12 is also 4 times 3. Could be another way to write the answer to that number. Notice how 4 is in our sum. The answer for the second one to get 24 is 8 times 3. Notice that 8 is in our second term within the sum. 10, 11, and 12 adds 33 is also the same thing as 11 times 3. Notice that 11 is also in the middle term. Hopefully you're able to pick up on the pattern for the last one, that it's also 17 times 3, and 17 is your middle one. So a conjecture that you could make based on the pattern that you are seeing is the sum of any 3 consecutive integers is 3 times the second number in that sum. So again, in this specific instance, all of your numbers have to be in order. They have to be in increasing order. And because you're adding 3 numbers, it is 3 times that second number. So we're going to test that on another set of numbers, knowing what the conjecture is in mind. So let's try with -1, 0, and 1. You add those together, you get 0, and we're going to take that 0 times 3, which is our middle number, and that gives us the exact same thing. So it works with both positive and negative, because the rule for integer is just a whole number that could be a positive or negative. Now doing triple digit, you add 100 plus 101 plus 102 to get 303. And we're going to test and see, does 3 times 101 give us that? And yes, it does. So that would be a way to prove the conjecture true, following it onto other sets of numbers. All right, so a counterexample would be a way that you can find if a conjecture made to be false. So let's say on that last one, we found a set of 3 numbers that doesn't follow that rule. That would be a counterexample to prove that the entire conjecture is false. We would then need to go back and re-look at how we came across that conjecture and how we can refine it to be true for all examples. So let's say a student is making the following conjecture about the sum of 2 numbers. And we're going to find the counterexample to prove that this student's conjecture is false. The sum of 2 numbers is always more than the greater number. That would kind of make sense. You're taking 2 numbers and adding them, you would think that they would get bigger, right? Well, in order to find a counterexample, we need to find a sum where that is less than the greater number. Negative numbers are still numbers. When you add -2 and -3, you get -5. Now, yes, just the 5 is greater than the greater number, which is just 3. However, on negatives, it's opposite, where the bigger the number for negative, the less it actually is. So -5 is actually less than -2 and -3. So your counterexample to prove this conjecture false is -5 is not greater than -2. All right, moving on to deductive reasoning. Using facts, definitions, accepted properties, and laws of logic to form a logical argument. When we did inductive reasoning, we were looking at patterns that we observed within a couple different examples. This one is actually using hard facts and definitions and formulas and things that are accepted to form a logical argument. So one of those laws of logic is called the Law of Detachment. If the hypothesis of a true conditional statement is true, then the conclusion is also true. So you're looking at the whole conditional statement, but if just the hypothesis is true and you know that the whole conditional statement is true, then the conclusion must also be true. The law of syllogism is another example that connects 2 different if-then statements where the conclusion and the hypothesis match up. So notice how in these different colors, you have an if P then Q, then an if Q then R. Those Qs are the same statement. They're in the same color, but they're just put in different spots in these conditional statements. So if your first conditional statement, if P then Q, if that is true, and then you can also say that Q then R is also true, then you can make a brand new conditional statement using the hypothesis of the first one and the conclusion of the second one, and that would also be true. So you're kind of taking 3 different parts and connecting them. If P then Q, if Q then R, then you can say if P then R, connecting all the way to the end. Okay, so if 2 segments have the same length, then they are congruent. You know this by BC is equal to XY. Let's use the law of detachment. What statement can we make? Right, so if 2 segments have the same length, that is your hypothesis, then they are congruent. That is based on the definition of it being congruent. So if this is true, then we can do BC is equal to XY. So because that satisfies the hypothesis of a true conditional statement, then the conclusion is also true. Based on the definition of it being a congruent segment, you could say that BC is equal to XY because those 2 segments have the same length. And that's what that congruency symbol right there is. So if possible, use the law of syllogism to write a new conditional statement that follows from the pair of statements. So part A, if x squared is greater than 25, then x squared is greater than 20. If x is greater than 5, then x squared is greater than 25. So for part A, if the hypothesis for P is true, then the conclusion of Q is true. That whole thing is true. If Q, then R. Then we can connect if P, then R. So notice how we are looking at the conclusion of the second statement of the hypothesis of the first statement. So the first statement is the x squared is greater than 25. That matches up with the conclusion Q. That's also going to match up with the hypothesis of the other statement. So even though the statements themselves are not written in order, you are trying to find which hypothesis matches the same conclusion. And for this example, it's the x squared is greater than 25. So the order doesn't matter whether you can lose the law of syllogism or not. Just find a matching hypothesis and conclusion. So you could then say in a new conditional statement, if x is greater than 5, because it's your hypothesis P, then x squared is greater than 20 is your conclusion R. You can put those two together in a brand new statement. If x is greater than 5, then x squared is greater than 20. So part B is going to be the exact same thing. We're going to look and try and find which hypothesis matches the conclusion of the other one. If a polygon is regular, is a hypothesis, then all angles of the interior of a polygon are congruent. That's a conclusion. In the second statement, if a polygon is regular, it's also a hypotenuse, then all sides are congruent. Notice how the reds are the ones that match, and they are not in the hypothesis and conclusion part separately. They are both hypothesis. So this is not using law of syllogism. You cannot say that if two hypotheses are true in each statement, then you can put the conclusions together. These may both be separate true statements, but you cannot combine them with conclusion and conclusion as a new conditional statement. Okay, the law of syllogisms has to match one hypothesis and one conclusion of two separate statements, not two hypotheses. So what conclusion can you make about the product of an even integer and any other integer? Well, the product is the same thing as multiplying. So we're going to look at a pattern of a couple different examples between multiplying an even integer and any other integer. So for this example, evens are 2. So we're going to just look at -2 times 2 to be -4. Okay. -1 times 2. Again, 2 is still our positive number. So we're going to multiply those and get -2. 2 times 2, 4. Okay. 3 times 2, we still have 2 as our even integer is 6. -2 times -4 is 8. Again, we are just multiplying different sets where one number must be even. They could both be even, but I'm looking through different examples where at least one number is even. And let's look at what happens to the answer. Any even integer times any number is always going to be an even answer. So look at all of our answers. -4, even. -2, even. 4, even. 6, even. So anytime you multiply an even integer times any integer, no matter what, it's always going to be even. So you could set some variables as n and m as your any integer, and we're going to use deductive reasoning to show that the conjecture is true. So 2 times any number is an even integer because any integer multiplied by 2 is even. 2 times any number times any other number represents the product of an even integer, 2n, to make an even number, and any integer m. You're putting the 2 and the n together because you know that it's going to be even. So if you multiply 2n times m, that product of 2 and an integer of n times n is always going to be an even integer. Okay? So one thing that you're going to frequently use for inductive reasoning is to make conjectures. You could also be using deductive reasoning to show whether they're true or false, but you're going to need to know which type of reasoning to use. So again, inductive reasoning is to find conjectures. Deductive reasoning is looking at concrete examples. All right, decide whether inductive reasoning or deductive reasoning is to be used on the conclusion. Explain your reasoning. So each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up in the air, it will return to the ground. All reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. Okay. So looking at the first one, each time Monica kicks a ball up in the air, it returns to the ground. That's a conditional statement. That's based on a pattern. Every single time she's doing it, this thing is happening. This is using inductive reasoning because it's using patterns. Every time she does this, she is noticing this pattern. Part B, all reptiles are cold-blooded. This is an if-then statement, but you don't see the words if or then. So if an animal is a reptile, then it is cold-blooded would be your if, using the words if and then. It's just a different way to rewrite a conditional statement. Parrots are not cold-blooded would be an example of a negation. You are inserting the word not into a type of conclusion from your first statement. And the second one includes a negation of the hypothesis. So this is saying if P, then Q. If not Q, then not P. This would be an example of deductive reasoning. You are using logic. Facts about animals and the laws of logic are used to reach the conclusion. And that is the end of the video.